Hello everybody, and welcome back to Math 105. Plan for today is we are going to finish off Standard 19. As far as office hours go, for this Thanksgiving week, I'm only going to have my office hours on Monday, plus the kind of like drop-in times during regular class. You can kind of come in, ask questions. If groups come, we can talk about whatever you all want, do some examples. I will not be holding my office hours Tuesday through Friday, though, mainly because it's Thanksgiving. I don't expect anyone to really want to show up anyways. Plus, I'll be potentially doing some travel during those days. As far as homework goes, Standard 18 quiz, the one on elliptic geometry, is due Monday the 23rd, which is Monday of Thanksgiving week. Today, if you're watching this video on the day that it's that you're meant for the Standard 18 quiz due Monday the 23rd of Monday of Thanksgiving week, the day that this class is intended to be for. And the Standard 19 quiz is going to be due on Monday the 30th, the Monday after Thanksgiving. Just giving you a long time because I don't want you to have a quiz due like the day before or the day after Thanksgiving. That's just cruel. Also, if you're watching this early, keep in mind Standard 16 and 17 quizzes are due the Friday before Thanksgiving. So, day or tomorrow, depending on when you're watching this. Or potentially it's past. Hopefully you didn't miss it. As a reminder, today we're just finishing Standard 19. The week after Thanksgiving, Monday and Wednesday, we'll do Standard 20. And then Friday after Thanksgiving, we'll do the last midterm of the semester, which will be your last, which will be your last midterm, which will be over every standard before the final, which will also be over every standard. Give you some chances to get masteries in whatever you still need them in. So, as a reminder, Standard 19, we are talking about hyperbolic geometry, where hyperbolic geometry is just kind of a blanket term used to refer to any model of geometry where the hyperbolic parallel postulate is satisfied. Where the hyperbolic parallel postulate says for every line L and for every point P that's not on the line L, there exist at least two lines M and N that pass through the point P and that are parallel to L. So this was different from the parallel postulate versions we've seen before, and that the Euclidean version said there should be exactly one line through P that's parallel to L. In the elliptic parallel postulate, there's no lines passing through P that are parallel to L because the elliptic parallel postulate says parallel lines don't exist. So this postulate refers specifically to models of geometry where more than one line exists passing through the point P that's going to be parallel to L. And the particular model we were looking at in Standard 19 is the Poincare disk model, which I realized after I did the last video, we didn't talk about why does this even satisfy the hyperbolic parallel postulate. Well, before we do that, let's talk about the two lines that are okay to have in the disk model, Poincare disk. The first type of line that we can define to be a line is just a diameter of the disk, a straight line going from one point on the disk to the opposite point. I can't just draw a straight line from here to here because those are not opposite points. They have to be lines that kind of have the maximum possible length going down the middle of the disk. The other type of thing we're going to call a line is a circular arc that is perpendicular to the outer circle. So in other words, what that means is it's going to be kind of part of a circle that's going to intersect the outer disk at two right angles. And what I mean by circular arc would be if we were to continue it outside of the disk, it would eventually make a full circle. So, kind of introduced this yesterday. I realized after the video, we didn't talk about why does this satisfy the hyperbolic parallel postulate. Well, let's draw a quick little example to see if we can find out why. Just a quick example. Let's say that this line here, this diameter, is going to be our line L. And let's say you've got a point P that's way up here. If the hyperbolic parallel postulate is true in this model, we should be able to find multiple lines that pass through P and are parallel to L. And in fact, I think we can do that. I think we can draw one that looks like this. Let's call this one M. And we can draw another one that's going to look something like this. Where here, M and N are both circular arcs, both of which happen to pass through the point P. They're both going to be lines in the sense that they're type 2 lines in this model. And both M and N are parallel to L, meaning neither of these two arcs, M and N, are going to intersect the line L. So in this model, it is totally possible to have, given any line L and any point P not on L, there's always going to be multiple lines passing through P that are parallel to L. In fact, in this model, there's going to be more than two. I could draw another one if I wanted, something like this. I don't know, what do I call this one? M and call this, no, not P, I've already used P. Call this line P. In fact, there's infinitely many lines in the Poincare disk model that are going to pass through P and yet still be parallel to L. It's kind of nifty if you ask me. But in particular, there's at least two, so the hyperbolic parallel postulate is satisfied. So what I want to do for the rest of today is to do something similar to what we did in Standard 18. I want to kind of go through a list of properties, like the exterior angles theorem, the alternate interior angles theorem, like we did in Euclidean or with elliptic geometry, and see, do these properties that hold true in Euclidean geometry still hold true in the Poincare disk model, in this model of hyperbolic geometry. So let's take a look. So the first thing I want to talk about is triangles, and in particular, how do triangles behave in the Poincare disk. So let's see if we can draw an example of what do triangles generally look like. Well, I'm going to try drawing one out here. Let's see. Go ahead and make one line be a diameter. You can draw triangles where all three sides of it are made up of circular arcs. You could have triangles where all three sides are diameters. I'm going to do one where one side is a diameter and two sides are circular arcs. All of which, remember, are still lines. Let's have that be make up one of the sides of the triangle. Let's see. We'll put an arc that does this. And we'll have another arc that does this. And here is going to be our triangle here. A, B, C. Doesn't maybe look like your typical triangle because one of the sides is straight, but from B to C is straight, but from A to B and from A to C are curved lines. Well, this is still going to be a triangle in that it's defined by 3 points of intersection, A, B, and C, where we have these three lines kind of meeting up with each other. And so this right here is still going to be a triangle in this model. Even if you might look at it and say, Dr. Bursell, that doesn't look like a triangle. It doesn't look like a triangle in Euclidean geometry, but it's totally a valid one in hyperbolic geometry, in this Poincare disk model, to be specific. So let's take a look at the angles in this model. If you notice, all the angles look to be pretty small, especially at the angle of the angle A. And in fact, if we were to try and add these angles up, just eyeballing it, I tried to draw it so that they would add up to about 150 degrees. Whoa, Dr. Gerstel, you telling me triangles in this model don't have to have 180 degree angles? You better believe it. So in hyperbolic geometry in general, all triangle sums angle sums, I should say, excuse me. Meaning if you take any triangle and you add up the sum of all the angles, how big they are, you're always going to get a total that's less than 180 degrees. No matter which model you're looking at, they're always going to add up to less than 180. Which is kind of bizarre that they have to add up to less than 180. Because if you remember, in elliptic geometry, all the triangles there had to add up to more than 180 degrees. In particular, we saw an example where we had like 2 right angles in a triangle. So, just like how elliptic geometry is different from Euclidean geometry in terms of given any triangle, what is the sum of the angles, it's going to be different in hyperbolic geometry, but going the other way. In elliptic geometry, all triangles add up to angle sums are more than 180 degrees. In hyperbolic geometry, they're always going to be less than 180 degrees. Whereas in Euclidean geometry, they're always going to be exactly equal to 180 degrees. Just all triangle angle sums are less than 180. They can also be different from each other. You can add to different totals. Less than 180 degrees. So like in this, so for instance, I drew a triangle whose angle sum was about 150 degrees. I could also draw triangles in this model whose angle sums are smaller. I could draw one potentially whose angle sum is 120 degrees. Generally, if I were to want to make a triangle with smaller angle sums, I would make one where all 3 of the sides are made up of these circular arcs. So instead of having this diameter here, I could make a triangle with a smaller angle sum by doing something like this. And now, A, B, C are all going to add up to even smaller angle sum than what I had before. So, triangle angle sums are different in kind of the opposite way from Euclidean geometry here, in the opposite way that they were in spherical geometry, back in standard 18. So let's talk about a few other results from Euclidean geometry, including the ones we talked about in the previous standard. So in particular, I'd like to look at the exterior angles theorem and see if it works in the alternate interior angles theorem, and see if these two theorems, these two propositions, still work in the Poincare disk. So we're going to ask the question, which results still work? So we'll start with the exterior angles theorem. And just as a quick reminder, for each of these, I'll give the Euclidean geometry version of a picture of what they all said. The Euclidean version of this said, if you have a triangle ABC, and you took an exterior angle to this triangle, say the angle BCD, what the exterior angles theorem said is that the exterior angle BCD has to be greater than both of the interior angles opposite from it. So in this case, the angle of B, angle ABC, and it would have to be greater than the other angle opposite from it, the angle at A here, angle BAC. Let's see, in looking at a picture in Euclidean geometry, if it looks like this theorem is still going to hold. And we'll make a general statement here. We'll just make a statement about Poincaré disk. So here, I'm going to draw a quick triangle. Let's see. I have ones. We'll try and do ones that look something like this. So here will be our point A, here will be our point B, here will be our point C, and let's put another point over here, D. And the question I have is, if we look at the angle ACD, is the exterior angle, and by exterior, I mean exterior to the triangle ABC, is the exterior angle ACD greater than let's say its remote interior angles. Angle BAC and angle ABC. So in other words, is this angle right here going to be greater than that angle and that angle? Well, certainly looks like it. ACD looks like an obtuse angle to me, whereas BAC and ABC look pretty acute, smaller than right angles. So I would say, yes, it certainly looks that way. And in fact, the exterior angles theorem in general is going to work over the Poincaré disk. So the exterior angles theorem works from Euclidean geometry, still holds true in this model of hyperbolic geometry, which is interesting because if you recall, this theorem did not work in spherical geometry, but it does still work in the Poincaré disk model, which is kind of cool. So how about its friend, the alternate interior angles theorem? As a reminder, what this theorem said in the Euclidean version is that if you have two lines, L and M, and if they're met by a transversal like this, such that this angle and this angle are equal to each other, so in other words, if angle ABE is equal to angle BEF, angle AB equals angle BEF, then L is parallel to N. This double vertical bar, by the way, just means parallel. So if angle ABE is equal to angle BEF, then these two lines have to be parallel. We saw that this theorem was one that did not hold true in spherical geometry. Let's see if it looks like it's going to hold true in the Poincaré disk. So let's see. Let's have two lines. Here, we're going to just do an example that only involves circular arcs. And have our transversal also be sort of this circular arc that comes down the middle here. So here will be our point A, here will be our point B, here will be our point C, here's going to be our point D, here's going to be our point E, here's going to be our point F. And I tried to draw this in a way so that angle ABE and angle BEF are supposed to be right angles, basically. And here, if we call this line L, this circular arc along the top, and this circular arc along the bottom, M, we can see here that angle ABE is equal to angle BEF. They're both right angles. At least that's how I tried to draw it. So here's my question. Are lines L and M turning out to be parallel here in this picture? Well, they're not parallel in the sense that they go in the same direction, but the definition of parallel Euclid uses of they never intersect each other, no matter how far out you extend them, still works. This line L here, this circular arc, does not intersect this circular arc M in this case. So we can say L and M are still parallel to each other. And in fact, just like the exterior angles theorem, this alternate interior angles theorem that says anytime these alternate interior angles are equal, the two lines have to be parallel, turns out this theorem does hold true over the Poincare disk. So, again, same ordeal. The alternate interior angles theorem did not work in spherical geometry, but it does still work over the Poincare disk. So, we've now had two theorems that work in Euclidean geometry and in the Poincare disk, but not in spherical geometry. So you might be thinking, Dr. Gerstel, are there any theorems that work in Euclidean geometry but not over the Poincare disk? In fact, there is kind of one big, well, other than the theorem that said triangle angle sums are 180 degrees. There is, in fact, another big theorem that works in Euclidean but not over the Poincare disk model, or the spherical geometry model for that matter. And that's going to be one of these big old main theorems that I'm sure you all are familiar with, the Pythagorean Theorem. Where the Pythagorean Theorem, I'm guessing you all remember, we've talked about it a few times before, says that if you have a right triangle, like so, then the hypotenuse, the side opposite the right angle squared, has to be equal to a squared plus b squared. Meaning the length of the other two sides, when we square them and sum them together, will give us the length of the hypotenuse squared. So this is, forgot to write down, this is the Euclidean version of the Pythagorean theorem. Let's see if the same thing holds true in the Poincare disk model. So I'm going to draw the disk here. Let's see. We'll make one arc that looks like this. We'll make one arc that looks like this. And we'll make another arc that does something like this. So we're going to have a triangle here. I'm going to let A refer to this side, B refer to this side, and C refer to the longest side, the hypotenuse, so to speak, the side opposite the right angle. And here's my question. A squared plus B squared is going to give us C squared. And it turns out it's not going to be the case. Hard to see from the drawing. This is one that you can't really visually see very easily. But in fact, what's going to happen is that C squared will be greater than A squared plus B squared. So why is that? Well, the reason why is because the fact that A squared plus B squared is equal to C squared, we didn't prove the Pythagorean theorem, the Euclidean version, but a big part of this comes from the fact that that the angle of how do I do this? The angle opposite A plus the angle opposite B equals the angle opposite C. So in other words, this right angle is equal to the sum of the other two angles. Why is that? Well, in Euclidean geometry, we know that these three angles have to add up to 180 degrees exactly. This angle is 90 degrees, so the other two angles have to add up to 180 minus 90 degrees, which is 90 degrees again. So here, angle opposite of side A plus the angle opposite side B is equal to the angle opposite side C. Whereas over here, in the Poincare disk model, the angle opposite C, or the angle opposite A plus the angle opposite B is going to be less than the angle opposite C. Certainly doesn't look that way. It certainly doesn't look that way, but that's just because this is not the best of drawings. The reason why this is we know that the three angles in this triangle have to add up to something less than 180 degrees. Because that's what we talked about earlier. If angle C is 90 degrees, if the whole thing adds up to, say, I don't know, 150 degrees, then the angles opposite A and B would have to add up to 150 minus 90, which is only 60 degrees. The fact that all three angles add up to less than 180 tells us that if one angle is 90, the other two have to add up to something less than that. Otherwise, all three angles would add up to something 180 or greater. So the Pythagorean theorem is going to be an example of a theorem that works in Euclidean geometry but not in hyperbolic geometry in general. In particular, it's not going to work in this Poincare disk model. And that's going to do it for standard 19. Just to give you a sense of what's coming up, standard 20, we're going to be comparing the behavior not of triangles, but of quadrilaterals in the three systems of geometry we've seen: Euclidean geometry, elliptic geometry, and hyperbolic geometry. So that'll be standard 20, which will be Monday and Wednesday's classes after the break. I hope you're all doing okay. I hope you're all staying healthy and mentally sane. I encourage you to try and relax a little bit over Thanksgiving. If you can, have some fun with your family, but in a safe, socially protected way. And I will be back with you again after Thanksgiving. Take care. Be cool. Stay cool. Except for you, Jonathan. You're already too cool.